Good day to you. This is Galactic bringing you another extra super hyper deluxe excursion into the universe. Where we're at now is going into the inner limit, and we're going to actually get there. Science has been trying to get to two locations, but one of them is not a locality. The other one is, and that's what we're going to concentrate on. So let's begin with the word locality, a very important word in the philosophy of science at the quantum level. The term locality does refer to the paradox. And these glasses, I lost my crap glasses. That's all caps C-R-A-P, the name of the company. I lost them, unfortunately. They served me well for close to 3 years. But these, I can get 25 pairs of these for the same price as the crap glasses, and I like them better. And I've been told, down at the cafe where I hang, that I actually look pretty cool. Of course, it is a combination of the haircut. You notice I got a military side and a little on the top. That's how my father had his haircut. He had a crew cut most of his life, because back in those days, men liked to wear their hair short, and if you were a Major League Baseball player, you might indeed have a crew cut. Not many had a crew cut, but my father did. He always claimed it was the best haircut of all. I saw no reason to argue with my father about anything. I never found him to be wrong about anything. Although, just as an anecdote before we begin, so there's a little humor here. By the way, we are going to have a riddle and skit format that's going to be a regular feature. Try to attract more attention in some carnival act way. Well, you know, we are human and we do want to have fun. We subscribe to that here at Galactic, so riddle and skit format, expect that. Now, before I go on with my anecdote, I want to bring us up to speed. You may be wondering what's going on. You know, where's the fluff? Where's the beef? I don't see any diagrams. There's no more GeoGebra. You don't show anything. This is supposed to be geometry, okay? So I am humble. I'm contrite. I'm working hard. But there's been a financial, bottleneck, I think is the term. So in July, I expect to have a broadband connection. All of these videos for the past couple of few months have been uploaded using a Wi-Fi connection, for which I pay $10 a month, which is reasonable. The broadband connection in my location runs about $80 a month, so I had to suspend that for a while. So the live streaming, which I think is critical, that was one of my original hopes, was to have an interactive format where you can reply in real time or ask questions in real time or state how much you just detest something or other so maybe I could change it, or just, ridicule me. If you're a troll, I won't accept it as ridicule. You will get a response. Whatever comment you leave, no matter how, ornery or lugubrious it is, I will give you a cogent and accurate reply based on the tenor of your question. So expect to get fire for fire, because I don't back down to anything or anybody anymore. Now, so far, that's been like tilting at windmills, and I have given some rants on things like Israel and governments and the state of scientific. I won't use one of those funny words I like to use when I get emotional. That doesn't really fit in science, but it sure does fit in fun. Now, we are trying to unify those two things. So on a related front, not only do we expect to have live stream in July, but there will be a new format. I do expect to have a plethora, one of my father's favorite words, a plethora of diagrams, because you're going to want them, even if I insist, as I do, but sotto voce. You don't really need them, and the reason is you should be doing this all in your head. Now, I myself much prefer to see diagrams when I'm reading, because, there will be diagrams. Now, I'm coming up to speed on the latest version of OBS. If you are interested in open source software, I do use a Macintosh, and that's a small niche of the market. I have tried also to address those of you who use phones, Android or iPhone, for listening to this. I believe it looks fine. It used to. I assume it still does, but I haven't resumed the testing that I probably should be doing now that I have not only a new version of OBS, which is the recording software, but I was using iMovie in order to edit the recording before releasing it to YouTube. And there are various editors of very high quality, a couple of which, at least I'm limited to the Macintosh field, but generally speaking, it's comparable, because Apple does like to keep up with the industry. It's a wonderful platform. But I have switched to something called DaVinci Resolve, which is a much, much more powerful program with features that I probably won't need at least for a while. But I do have a projected improvement curve for what you're viewing. Again, I apologize. I am wearing these because of allergies, which make eyes look a little bit something you don't want to look at for a half an hour, really. If you could avoid looking at them, well, you can avoid looking at them with these marvelous oversized lenses in the way of my irises, which, it's not really, the iris doesn't change color, but whatever the white area around the iris, those of you who know about the human eyeball would just leave a comment. Here's the word you're looking for. You don't need to look it up. Here it is. Well, I appreciate any comment you would care to leave. Positive or otherwise, I'm desperate for any kind of input. In the name of science, I actually have no personal need for that, although I think we all would like drum our fingers there. You don't? Yes, of course I do. I'm human. However, I have adapted to my lonely circumstances out here in the middle of the northern Sonoran Desert. It's a good place to do this kind of work. Not so good for astronomy. I would like to move, and I may be capable of that by the end of this year, in which case I will probably move north, where the skies are clearer in general. Well, the sky has a greater clarity, as opposed to the pollen basin of Northern California, so that's why you're not looking at my eyes. Now, that having been gotten out of the way, let's begin with our presentation today, which I think is an excellent place to begin in homing in on cutting-edge science. Now, again, to be absolutely sure of what we're saying, I'm highly specific, and in science, you do, in the scientific discovery process in which we're now communally involved, you and I anyway, it is necessary to, first of all, maintain continuity, but you do have to define first continuity toward what? What is the goal? There does have to be a very specific goal. In philosophy, it's much more open-ended. And we necessarily are touching on philosophy now, actually more than a touch. The nature of natural philosophy, as science used to be called, was the focal point of science, was to get understanding. That is no longer true in the sense that it had been in the 19th century and earlier. Now today we're going to be discussing someone from the 18th century. This is right on the heels of Newton, Leibniz, and Huygens. Three of the biggest names in the area that we're covering. So let's get into a little bit of synopsis and summary so we know where we're at and we know where we're going. The focus of attention had been originally astronomy, which is a huge subject. From there, it got more towards cosmology, which is the fave-rave today. Physicists believe that they have some new insights into something which is brand new for just about exactly a century. Just about exactly, yes, that's a very scientific way of speaking. We discovered a universe that was much bigger than the one that had been known to the ancients due to the effects of the Mount Wilson telescope discoveries made by Edwin Powell the Major Hubble and a space station, an orbiting space telescope was named after Edwin. Probably if we had inherited some of the British habits, he would be called Sir Edmund. Edwin. Sir Edwin. Not German, not Edwin, when you're saying the name of Schrödinger, which I hear a lot of East Coast pedants purposely pronouncing that wrong, as they do Gödel and some other names. But his first name would be Edwin. The W in German, of course, is pronounced as a V. All that being aside, where we're at is no longer astronomy per se, although we're coming back to that. That is how we will end. Now, the way we're approaching science in general, in order to focus down to our topic, certainly today, we are at the quantum limit. And that is necessary to get to that level because the photon, of course, is quite small. It is considered to be the smallest of the particles, but my view of particles does not match that of the standard model of particle physics, which treats everything as a particle. And just so you have a little bit of insight into that, if you're not too familiar with the standard model of particle physics, they have about 26 pseudoparticles, of which 2 are actually particles according to my much more correct morphological classification system. The proton and the electron are the 2 particles. We're going to be dealing with that today directly, and the way we're going about it is geometrical, which is an out-of-date, virtually archaic method of approaching science due to the absolute domination of mathematical logic, which has a pitfall, and it also has a black eye. That is, of course, the nature of linear geometry with respect to what was discovered in the 20th century, that the universe doesn't give a hoot about our linear geometry because it uses an integral number system and an integral geometry. The advantages of switching to that geometry, could it be done, would be, first of all, the acquisition of curvature, which we do not have, and the Greeks gave up, and nobody's been able to solve it since. I've solved it. And one of the major additions to our arsenal of terminology, which we're now capable of utilizing in the formulation of scientific propositions, is a term which used to dominate the natural philosophy discussions in the 18th century. All 4 of the major names of that time dealt with a term called continuity. Continuity. You virtually never hear that word anymore because mathematics has gone around it. Continuity is now ignored. Well, it can't be, for the same reason that we can't ignore geometric curvature, which our linear algebra is incapable of addressing except with the calculus, which in a sense is an inaccurate tool. Now that would be at least virtually violently argued by most of mainstream top physicists. That's okay from their point of view, and from my point of view, objectively, they're entitled to their opinion. It works for them, they get paid, the government gets what it wants, and the world rolls on. I am not involved in that at all. I'm dealing with truth, not expediency. I'm not interested in the comfort of my feet around the hearth at night, making money by lying to people in order to satisfy their baser instincts, in order for them to feel better about what the government is going to do with the knowledge it gets from physics, which is never good. So, having give each of these topics I'm touching on lightly, I've covered in several lectures in my training phase over the past 3 years, making 560 video presentations so far. The focus has changed because the reason I started producing on YouTube is because I came upon a discovery vector, which is really one of the goals of any true scientist. It's almost a dream, like getting to the moon. If you're looking at the moon and you're dreaming of becoming an astronaut or cosmonaut, as they should be called, since the since the commies got into outer space first, they should be called cosmonauts, but we're Americans, we do everything the way we want, and they're astronauts. Well, a scientist wants to be a discoverer if possible. It's not likely statistically. And so this is rather, certainly was unexpected to me. And what I did discover was a new geometry, which is simply the integral geometry, which has its own number system that's also integral with respect to linear numbers. This gives us access to continuity, because the closed line, and think of that as the circle and the sphere, those are the two closed lines. They're called closed because obviously there are no endpoints on a circle or a sphere. And that actually is a very deep-seated principle of the universe that's embodied in that kind of line, and that term for that is continuity. Now, to go back to the 18th century, this would be the 1700s. This is the century in which Newton died, and Leibniz died, and Christian Huygens died. And that left just one man who was a young man when these three men were basically on their way out or already out. And Ruđer Josip Bošković grew up in Croatia, a Slavic-speaking country, and he became the foremost scientist in Europe. He didn't have a lot of competition. With the demise of Newton, Huygens, and Leibniz, it more or less left a vacuum. Now, there is no real vacuum in the progress of science because it is a continuous process, and that's an interesting way of putting it. But the main topic covered by all of these men was the wave-particle duality, among other things. Another aspect of reality they were dealing with was infinity. And infinity is the key term in understanding continuity. So let's define continuity first. And then we're going to get into the Bošković force curve, which is so profound, it overshadows all of my work, except in a supportive sense. It's a little unfair. It's comparing apples and oranges. I discovered a geometry. What Bošković discovered was the force balance system of universal physics. That is being recognized now. You might ask, why was it not recognized in Bošković's day? He's a relatively little-known name, although unrightly so. It's just that his perception was not understood by anyone else. He was quoted, and he is well known to the top physicists. Tesla knew of Bošković. There's even a photograph of Tesla with Bošković's opus magnus, and I can say that because it was written in Latin, Theoria Philosophiae Naturalis, which means a theory of natural philosophy, which means a theory of science. In other words, basic. And so what was the nature of his basic insight? It's different from that of Newton, and it's different from that of Leibniz. It's not as different from Huygens' wave theory of light, which is now at the forefront, but it's a tied race with Newton, who thought of light as being made of photons. Now, we discussed that in the last presentation, Unimetrics 2. I'll be changing the abbreviation. Umeter is not really a very good abbreviation because it's hard to pronounce. Unimetrics, I'm just going to spell it out. What is that? It's a synthesis of Bošković's work using a new geometry, which gives us access to space-time in a brand new way, and access to the quantum paradox so as to understand it and, in fact, solve it. So we did a lot of that in the last presentation, and the reason for the current presentation series is to formally present all of the information insofar as is possible to summarize conveniently. There's always a trade-off between time and detail. Now, what I've been after the whole time, going right back to my days of astronomy when I just wanted to give tours of the universe and still wish to return to that subject, but the questions being asked by humanity and by science, these overlap of course, have to do with infinity and reality. at both limits, and there are two. This is critical insight, so don't think of this as just being some verbiage to introduce the topic. There are two limits that must be faced. The first one that was faced in science was the limit going out, you could say it that way, but actually both limits were discovered almost simultaneously in the first half of the 20th century. The outer limit is the one familiar even to the ancients. When you look into the night sky, you become aware rather quickly, even as a child, of a certain perception which is somewhat overwhelming, because the spherical extent of space increases rapidly because it's the maximum increase in volume on a linear distance. So when you look into deep space, your mind asks the question, seemingly automatically, where's the edge? Now, I've covered that in several video sequences over the past 3 years because it's such a critical question, because it's the beginning and end of science. Is going to be, and already is, on the nature of spatial infinite extent. Very difficult to conceptualize in the mind, particularly with mathematics. It simply cannot be reached. I've solved that problem. The problem of the rationalization of infinity, it's, as you would expect, a remarkably simple, straightforward answer, just marvelously elusive to the human mind thus far. So I consider myself to be privileged to be able to express what at the very least would be called an alternate point of view. In science, you'd really want to have provable extrapolations. You don't want to just build a fairy tale kingdom, castles of sand in the sky, such as the Big Bang and supermassive black hole theory is massively off course because of the nature of linear algebra, is simply incapable of dealing with this kind of problem, the problem of sphericity. Now, where it becomes most interesting is in contemplation of the universe, which is under contemplation. It always is. There's always a cosmology. So far, there have been, it's hard to say how many cosmologies they've been, but on the order of half a dozen, just roughly speaking. You could extend it or contract it. But today we only have one. It's the standard model of cosmological science, and it is focused, of course, on the Big Bang. That's actually not the most important aspect of the theory. The theory is based on a perception of expansion of space, giving space a characteristic that it can expand. That is an illusion, but it is a mathematically justifiable conclusion given the fact that the mathematics is already wrong. And it's not wrong in one context because of approximations to any degree of precision enabled by the calculus that turns out to be ineffective at the limits, because then you cannot get around the fact that you're using single componency numbers, which we call linear numbers, 1, 2, 3, 4, yes. But the universe uses the integral form of those numbers, and those are called proportional numbers. Again, remarkably simple. We have been using them. They're called fractions. But the universe actually uses whole number fractions. In other words, 2 over 1 is a two-component number, but it's equivalent to linear 2, because 2 over 1, since 1 is the divisional identity, as it is the multiplicative identity, those are the two inverse operators in spheric space, as I discovered. Well, then you can invert that, 1 over 2. Now because of linear thinking, these are linear numbers in relationship now. 2 proportion 1, order is important, obviously. 2 over 1 is not the same as 1 over 2. However, the distinction between those two numbers can be taken in one of two ways. If you look at the relationship between 2 over 1 and 1 over 2, we tend to reduce those in our mind to their linear versions. Now, in the case of 2 over 1, that's easy. because any number over 1 is itself in linear form. That's one way of saying it. But then 1 over 2 presents an interesting problem, which has 2 solutions, and that's the only reason it's a problem at all. We always think, I'll just say generally, of 1 over 2 as being a linear proportion. You can say that, and that does work in linear algebra. That 1 over 2 is a number that we consider to be 0.5. However, and here's where it gets interesting and remarkably deep very quickly, so hold on to your seat. Either keep an open mind if you feel it closing, or focus your mind if you feel it wandering away, but this is incredibly deep stuff. At the outset, this is where it becomes obvious that this is inductive science, where the problems in deductive science come at the end when you're formulating the equations and trying to work them out. But in inductive science, the problems come right at the start in coming up with a definition that is correct. Because whatever you define, you're going to have to prove. So it's easy to talk when you're talking inductively, which is why we have a little side room called philosophy. Now, natural philosophy, the older term for science itself, is much more broad-based in the sense that you're not limited to just fanciful notions. You're actually dealing with reality, but in terms which not necessarily are directly provable. So that would be philosophy, and Ruger dealt with that, but most successfully. But in the time frame that he was in the 1700s, his discoveries were so far ahead of their time that literally no one around him could utilize what he discovered. So that's what we're going to talk about today. This does have to do with infinity. So I want to start there, and we're heading now towards the Bošković force curve for universal physics, the dynamics of the universe. It's an energic system. It can be said, and it has been shown by Albert Einstein, you can conceive of the universe as pure energy. Now, when it comes to the proton, you encounter another philosophical problem. Because the electron is pure energy, but the proton has an effect on space. The electron does not have any known effect on space. It just hangs out in space, but itself does not appear to be a spatial object. It simply is there, but in a form that is not material. So to call it a particle requires some explanation. Is indeed the electron a particle? The key word here, in order to define that or answer that question accurately as we can, pending the proof, the electron is a particle for this reason. It has locality. Locality. Locality is a relative term. It's used in quantum mechanics to indicate a state of an object. It's also called position, and position is an extraordinarily important term in linear mathematics and geometry because position is everything. The limitation is that the position that you're computing is a position on a line. If it's in volume space, you have to use 3 lines, which are coordinated on the center, which has to have the number 0. Which is a very special number. It's actually null, but it turns out that all of the numbers taken individually, each one is null. It only has relative substantiality. Now we consider that to be real, and rightly so. There is such a thing as linear distance. Linear spatial separation is how we measure things, using linear numbers, which is a match. So we measure space on lines. And if you have two of them, you have something called the plane, which is actually a squared plane. It's not really, the plane could also be thought of as a circle, so that the entire space of the plane begins at a point and then the circle expands. Now that's 2D thinking. When it comes to using the actual number system for that form of the plane, you don't want to use sine cosine if you can avoid it. We have found no way to avoid that because a circle is a two-componency parameterization. Anything on a single line is a one-component parameterization. 1, 2, 3, 4, 1, 2, 3, 4. And the way it's conceived on an open line, a doubly open line, the other side is the negative numbers. But they're single component positions. Now, on the plane, you now have a two-number position. X and Y is how we generally designate that. In Bošković's day, that was called the abscissa, which is X, and the ordinate, which is Y. These are synonymous terms, but he did speak Latin, so... Now, in the Bošković conception, what he points out right away in his Teoria, which I read, he's very careful to compare his work with that of Newton. Newton, of course, had made an enormous impact on science. And by the time Newton was no longer with us, Bošković, of course, knew everything about Newton's work. He was the next generation after Newton. And Bošković also deals extensively, in summary form. It's actually fairly easy to read. You may have to look up a couple of terms which are repeated, such as continuity, to get an idea of what he meant by that. But what he points out when he compares his work with that of his two predecessors, Leibniz and Newton, the two men who discovered the calculus, that's not a coincidence. Rüger knew the calculus from both men. This is a remarkable statement, and I'm very happy to be able to state this. Bošković did not use the calculus. He did in his work, he was a professor of mathematics, basically affiliated with the Jesuit order, which was disbanded while he was in it, so he kind of had to do a little dancing there, and he ended up in France. But he traveled to England, he traveled all over Europe, and he was the most respected scientist in Europe. That's saying something. This is leaving out the pure mathematicians. I just simply won't talk about them. It's not that they're not significant, it's that just not particularly germane to our topic today, which is what? We want the structure of space. So did Bošković, so did Newton and Leibniz. So, the way we approach this is by looking first at what Bošković was focused on. And what he was focused on was the same thing that Newton was focused on. So what Bošković says about Newton is this. Newton discovered the fundamental nature of centripetal force. It's not precisely put that way by either man. Those are my terms, but I think you see that that does make sense. Because Newton was dealing with gravity. And gravity, of course, is a force that pulls in. It has been stated in many textbooks and is still stated today by such illustrious commentators as Dr. Sabine Hossenfelder that gravity is not a force. And you could say that. It does make sense in a certain context. I will be showing you that it in fact is a force. And that's part of what Roger discovered. But what he discovered, beyond what Newton discovered, is a second force that balances centripetal force. These are my terms, and I'm going to show that to you now. So those are the two forces that balance the universe. You cannot say any longer that the universe is defined on gravity alone. Now, our astrophysicists at the cutting edge are doing exactly that. They're treating the universe as if it were composed of gravity. You can say that, it's obviously true, but you're not saying enough. And that is the nature of Bošković's discovery. The second force, centrifugal force. Can you think of any examples of centrifugal force? You might think of the merry-go-round. I know I do, and I think most people do. Many presenters present it that way. Another way to understand or begin to comprehend, logically, formally, what is centrifugal force, well, you must realize that it's not going in, it's going in the opposite direction. It's a force that pushes out instead of pulling in. There's a mysterious aspect to gravity in that it pulls space in. We say that it curves space. That is one way to say it that's quite proper. I prefer to say it that way, although it goes deeper. Because when you say that you're bending space, that is, a proton bends space, it certainly does, or the electrons would not go into orbital shells around the protonic core. So there is a centripetal force being exuded. Einstein substantiated that, so we are permitted to speak that way, that space can be curved. But when you say that, you have to remember the Newtonian principle, that for every action, there is an equal and opposite reaction. Now, when space is being pulled in, you have to ask, being pulled into what? In linear conceptualization, linear geometry, the only way to geometricize that is on the grid, because we need the computable numbers, so we need 3 lines to make 3D space. That would be the square plane with a depth, which then makes cubic space. That makes sense to us, and it's worked for technology, so we think that it's going to work for the universe. You could say that it does. You can make it work with calculus until you reach the limit. And that is going in, that's the quantum limit, and going out, it's spatial volume infinity, which both of those are paradoxical. They can be solved by relating them together in the proper geometric space. You can rationalize both of the paradoxes together. So I'm going to cover that quickly today. We're already past a half an hour. I'm very sorry these lectures go on so long, but I think you see why. It's somewhat unavoidable, and I'm trying to master the art of summarization with the proper details so that you understand the proof. Without the proof, you're really walking on thin ice. So, we want to be sure that what we say is either proved already or is provable. That's as far as you can go, is to say that it's provable, but really that's not enough. You actually have to prove what you say for it to be science. Now, we want to substantiate the discovery made by Bošković, and he stated it this way. Sir Newton, well, you would say Sir Isaac, discovered a lot about the nature of gravity. Well, we know what particle controls gravity. It's the proton. Now, Bošković didn't know about the proton. It hadn't been discovered, so this was a major insight. He actually described the force curve, the algebraic force curve, which defines the atomic system. This is over a century before the atom was discovered. So that's being realized in top-level physics, and they don't know quite what to do with Roger's insights. So really nothing has changed since Roger's time. People have progressively, that is, progressively with time, many top physicists have examined Bošković's work and realized that he had a fundamental insight, but they simply could not use it. And what's truly remarkable to add to this is in all of the literature, and I've canvassed, well, I'll just say a good portion of the literature on Bošković's physics. There's not much, but even at the not much, it's still somewhat over. There's a lot. It's just relatively, there's not much about Bošković's force curve because no one knows what to do about it. But the comment that must be added is nobody has ever found any fault with it. That is almost unheard of in science at this level. That Bošković had an alternate dynamical physics, not the same really as Newton's, that is now known to be explanatory, but then the story ends. Nobody has developed it. Well, I know why. A major insight, I would have to say, certainly for me, I'm going to try to share it with you. What did Bošković discover? Well, he discovered the other force that's non-Newtonian. And it's centrifugal force. He did not call it that, though. He didn't use the terms centripetal and centrifugal. The reason I use those words is because they're the accurate geometric words for what was discovered both by Newton and then, in a much more synthetic and comprehensive form, really not negating much of anything that Newton said, but extending it and making it understandable. Well, that's what science is supposed to do, so Bošković's dynamic system for physics based on two balanced forces in the universe is a major insight that now needs to be incorporated into physics because it's a direct answer to all the questions we have right now. At the quantum limit, certainly, but I have also shown that with a proper approach geometrically to this dynamic force system of Bošković, you also can acquire, rather handily, a rationalization of spatial physical extent. In other words, the universe can be proved to have a finite characteristic. You have to say it that way. So to get into this, I want to tantalize you with a title to this, and it's going to have to be in the next lecture. We're going to cut this off at 45 minutes. But all of this time we just spent was to prepare you for what I hope and trust will be the most profound insight that you've ever had in your scientific life. It's nothing less than revolutionary. It's super miraculous and beyond anything that we characterize as miraculous, such as technology, which is certainly miraculous, but it also is a bit deceiving because we're still using the calculus, and the calculus is this sign of disease at this level. This only applies at the limits because it can be shown and has been shown exactly by technology that linear algebra can do anything. Well, we have to say it in a slightly different way now. Linear algebra with the calculus can do anything on Earth. And that's a very abbreviated way of saying that we're no longer dealing with Earth. This is not Kansas anymore. We're now talking about something much, much bigger. It's bigger in every way. The universe is not something that you can just suddenly realize that you know how the universe originated. Nobody knows that. And I don't think that anyone ever will, not in the near future. Because what you're trying to define is by definition indefinable. But in order to state that so that it can be proved, you have to go back to the mathematics. And then I found the proof that in order to deal with the universe as it actually is, which has an infinity on the outside, right? Well, it also has an inverse infinity at the core. What has misled physicists and anybody, including myself, exposed to the just obvious geometry of the universe, does the universe have a center? Be cautious before you answer. Remember, you'll always be better off with superpositional logic. It's a trick question because you have to switch to superpositional logic and you must give two answers, both of which will be correct in context. So having said that, can I substantiate it here? Yes, look at this. Does the universe have a center? Well, if you say no, that's what everyone else says. because, well, we have not discovered the center of the universe. That would be a point somewhere in the universe. There is no such point. How can you say that and be sure that you're saying that correctly? It's because it has no edge. And you can say that inversely. The reason the universe has no edge is because it has no center. Now that is a circular argument showing a direct relationship between the center and the edge. There cannot be a center or an edge because you need both to have either. That is the nature of superposition, and that's 45 minutes. Please stay tuned for the next presentation, in which case there will be no further bracketing information. That's why I am doing this in 2 parts. So you will be prepared for what you are about to see. Alright, I think I've introduced that sufficient. I have goose flesh on my arms right now. Okay, so it's real for me. I'm going to try to make it as real for you. That is what science does. This is Anagalactic, bringing you the secrets of the universe. Stay tuned. Keep looking up if it's night where you are. Or it soon will be night if it's not. If you have clear skies, get out and look. I don't care if it's for a minute, 5 minutes, a half an hour, or all night. It's the best time you'll spend on Earth. Alright? So stay tuned. We'll be right back.